Hello everyone. In this section, we're going to look at our fourth and final model variation. Now, there are absolutely more than this, but we're going to cut it here because there literally is an almost infinite number of applications of linear programming. And we have to continue on, but we've covered dietary, we've covered investment, we've covered marketing, and today we're going to cover a transportation example. Now these are most likely the four most common, and that's why we've covered them, but it's also why we're going to stop here, because we could continue on for weeks looking at different examples. Now, a transportation example is initially going to seem more complicated than the other examples we've looked at. It's only more complicated because it kind of alters our understanding of decision variables. So, as always, to begin, we're going to begin by reading our question carefully and attempting to understand exactly what this question is asking us. We're going to do it together. Before, in section 2, I move on and I'm going to solve it in QM. Eventually, we're also going to solve it in Excel. But for today, we're going to hold up with QM only because, as I said, this example is more complicated and I don't want it to be overly complex right now. I'd like you to understand the basic concepts before we try and translate that into Excel. So today's goal is to go through the question carefully, to understand exactly what's being asked, to formulate our objective functions, and also to look at our constraints. Once we've done that, we should have very little, if no problems at all, translating our equations into QM. Next time, we will look at doing it in Excel, but for now, our focus is to keep things relatively simple and to attempt to understand the base concepts. So, without further ado, let's look at the question put before us. The Big Buy retail chain ships televisions from 3 of its distribution centers or warehouses to 3 of its retail stores on a monthly basis. So we know right away that it's sending from 3 different shops or 3 different distribution centers to 3 retail stores. Each warehouse has a fixed supply per month, and each store has a fixed demand per month. This is, in the real world, relatively uncommon. But because this is our first example with transportation, they've kept it relatively straightforward for simplicity's sake. In the real world, it would almost never be fixed supply and fixed demand, but for now, that'll do. Let's continue. The manufacturer wants to know the number of televisions to ship from each warehouse to each store in order to minimize the total cost of transportation. Here's our first critical phrase. How many televisions do we ship from each warehouse to each store in order to minimize the total cost of transportation? Here we see a situation that, and we'll see later, is relatively simple, relatively straightforward. But it's an almost impossible situation for us to manually figure out. We're shipping not from 1 to 3, not from 2 to 3, but from 3 to 3. That's 9 different possibilities, each with varying transportation costs. So for us to figure this out manually would be very, very difficult. However, it is a relatively simple thing for the computer to do, because even at this level, while it's very difficult for us to manually solve, is still a very, very easy question for the computer to solve if we set it up properly. So we see each warehouse has the following supply of televisions available for shipment each month. So Cincinnati has 300, Atlanta has 200, Pittsburgh has 200. There are a total of 700 TVs available each month. Seems pretty straightforward. Each retail store has the following demand: 150 for New York, 250 in Dallas, 200 in Detroit. 600 TVs demanded. So we have 700 available. We have 600 demanded. Seems pretty straightforward so far. The cost of transporting televisions from the warehouses to the retail stores vary. Let's highlight that section. As a result of differences in modes of transportation and distances. Here again, they've kept things relatively simple. We haven't talked about what type of vehicle, we haven't talked about distances, only different shipping costs. So, in this situation, the shipping cost per television for each route is as follows. From A to A, $16, A to B, $18, A to C, $11, etc. So this is a situation where we have both warehouses and stores to consider. It's not quite as simple as what we've done, but it's not very complex either. So what we're going to do first is we're going to list our decision variables. Let's say, for example, we're going to call this Xij. And the reason I'm calling it Xij is because as we get more complex, it may become easier to look at this. Xij is very simply the number of televisions from warehouse I to store J. That seems a little complicated right now, but hopefully in a minute it becomes a little more clear. What we mean is I is equal to 1, 2, 2 or 3. We'll change this for simplicity's sake here. 1, 2, 3. And J is equal to A, B, and C. So we have a situation where X1A is equal to X1. X1A simply means from warehouse 1 to store A. Now, this is where things are going to increase in difficulty. Please try to follow, and if not, contact me. because from now, as we build on this concept, things are going to get much more difficult. This is difficult to teach to you in the classroom. It's much more difficult to do it online. The reason we've gone mostly to recorded videos is because as the concepts get more difficult, it may be necessary to watch these videos again. So we have a basic idea. X, for example, X3B would be from warehouse 3 to store B. X1A is warehouse 1 to store A. So what we're trying to do, and we saw earlier, we're trying to minimize Z, which is shipping costs, equal to 16x1A. And where we find that is $16 is the cost from shipping from warehouse 1 to store A, plus 18x1B. And that's from warehouse 1 to store B, the cost is $18. We're going to list all the costs for each of the 9 routes. And we're trying to minimize our total shipping for each, for the combined shipping of everything between each of those 9 routes. So give me 1 minute while I finish my objective function. Here we've entered 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different decision variables. And we see those decision variables right here. We see that X1A is $16, 16 X1A. We see that 17 is X3C. 17 X3C. All of these numbers correspond to one of these up here. Now we could say minimize Z equals 16x1 plus 16x2 plus 16x3 plus 16x1 plus 18x2 plus 11x3 plus 14x4. That's possible. But the reason we've done it like this isn't because it's easier. It's because it will be easier to conceptualize things like this in the future. This is still, and it doesn't seem like it right now, but this is still a very, very easy example. So what we're doing is, it's a little difficult now, but it will make things easier to understand in the future. Now, this is our objective function. Let's highlight this. Let's bold this. This is our objective function. Now, the first step, as we know, is determining our objective function, and we've done that right here. Now, what we have to do next is come up with our constraints. So let's look at our first constraint. What is our first constraint? New York, our first constraint is what TVs are available to ship. We cannot ship more than what is available. So what is warehouse number one in this situation? Warehouse number one in this situation is Cincinnati. We see that right here. Let's add a number here. 1. Warehouse number 2, Atlanta. 2. Warehouse number 3, Pittsburgh. 3. So our first constraint, let's call it, as always, C1. C1, and this is where we're going to represent our constraint for warehouse number 1. We know that 300 televisions only are possible. So how do we show that? For Cincinnati, what are our 3 variables? Well, let's say X1A, X1B, and X1C. The total from warehouse 1 must be less than or equal to what? Well, they have 300 available. So X1A plus X1B plus X1C. And this is kind of cheating. I don't want to do this, but hopefully it's a little more clear. X1 plus X2 plus X3 must be less than or equal to 300. We cannot ship more from number 1, warehouse number 1, than exists in warehouse number 1. That's what we've indicated here. The maximum shippable amount from that warehouse is what's available in that warehouse. And there's only 300 available in that warehouse. X1 plus X2 plus X3, that's just to show you we could represent these variables in another way, a simpler way. But for now, we want to get away from that because it will become more comfortable later. So let's, just because we're trying to make this clear, let's cross this out. Now we come down here and we're going to do C. Oh, guess we got to get rid of that now. C2. What's our second constraint? We know that C2, we only have how many TVs available to ship from Atlanta? 200. So X2A plus X2B plus X2C must be less than or equal to 200. And we see that here. 200 are possible to ship. So no matter what we ship to store A, to store B, to store C, it must be less than or equal to 200 TVs. That's what we've shown here. We'll repeat that one more time for constraint number 3. So in this situation, we check Pittsburgh. We see Pittsburgh again has a maximum of 200 TVs available for delivery. Cannot deliver more than that. It's all that exists. We look down here. From warehouse 3, Pittsburgh, we have to deliver to A, B, and C, but the total to A, B, and C must be less than or equal to 200. It can't be any more. So X3A plus X3B plus X3C must be less than or equal to 200. These are our first three constraints. These represent what is available to deliver. Now, we have other constraints, not just what's available to deliver, but what people actually want. We have three more constraints. So let's do that now. The first one, C4. We see in C4, how many does New York demand? New York is demanding 150. So the total must be less than that, more than that, or that. In this situation, they only want that. It cannot be more than that. It cannot be less than that. That is what they demand. So let's figure out how do we do that. So if they're demanding, store A is demanding 150. We see that here. So between, how can we get to store A? We have X, 1A right here, plus the second group going to A is 2A, X, 2A. And the third group going is X, 3A. And that must equal 150. So the goods shipped from warehouse 1 to A, 2 to A, and 3 to A must equal 150. Anything else doesn't work. That is our only possible solution in this situation. So let's repeat that for C5. We see that X, C5 is B, store B right here. So B requires 250. We see that right here. So the only ways to get there are 1B, 2B, 3B. So X, 1B plus X, 2B plus X, 3B must equal 250. The last one, C6. Here again, we see Detroit demands 200 TVs. Anything less is unacceptable. So how do things get to store number C? 1C, 2C, 3C. X, 1C plus X, 2C plus X, 3C must equal 200. Anything else is unacceptable. So now we have our total shipping costs for all 9 possibilities, and we have our 6 constraints. What is available from warehouse 1, what is available from warehouse 2, and what is available from warehouse 3. Plus, what is demanded at store number 1, what is demanded at store number 2, and what is demanded at store number 3. Once we plug all this information into the computer, what the computer will do is it will run every possible shipping solution. It will ship from store A or warehouse 1 to store A to store B to store C. It will ship from warehouse 2 to store A to store B to store C, etc., until it has only shipped as many as we have at each location, until it has satisfied each demand, and until it's done both of those for the cheapest possible price. Once we input this key information on page 2 into QM properly, and we hit solve, the computer will check every shipping possibility until it's satisfied each of those 6 constraints for the minimum possible price. Thank you, everyone. Join me next in the final session while we run through this example in QM. Thank you again for listening. Hopefully this is clear. If it's not, I'll try to make it a little more clear in the last section when we enter this problem into QM for Windows. Thank you again. In this, our final section for today, we're going to look at how to enter what I just talked about in the previous section into QM. Now we'll do it in Excel next time, but for today we're going to limit it to QM, only because what we did in the previous section, the way we aligned everything, will change slightly in this section. We have to kind of understand what I did in the previous section in order to label our chart properly in this section. We're going to, in some small ways, take the information given to us in the question and realign it so that it fits the presentation format of QM a little better. For that reason, I didn't necessarily want to rush through this and jump immediately into Excel because I don't want to lose anyone. Things will get harder in the future, but this is the baseline comprehension level. You need to understand this before we can move on to the next level. So please try to bear with me. As always, module, linear programming, new file. Transportation example. Now, how many constraints do we have? We saw during the question formulation that we have 6 different constraints. Variables. This is more complicated. We have 3 possibilities for delivery, 3 possibilities for receiving. That will be a total of 9 different variables. As I said before, this is a relatively straightforward, easy example. If we had, like a company like Amazon, if we had 120 distribution centers and potentially 5,000 retail outlets, our numbers climb exponentially. But the base idea remains the same. Amazon and large companies like that use programs like this all the time to minimize their shipping costs. They would run these examples, but they would run them at a much higher, much more complex level. This is real life, applicable usage stuff. But it's in real life, the only difference is it would be more complicated. Not 3 distribution centers, not 3 receiving points, but significantly more than that. And we'll build on that in the future as we move closer and closer to real life examples. So we have 9 different variables. And the key here is we're trying to minimize, not maximize. It's very important to remember we're trying to minimize our costs. We hit OK, and we allow QM to formulate our table. So we're trying to minimize, and it's a transportation example. Now, what I'm going to do is in our question formulation, we labeled these XI, XIJ, X1A, X1B, X3B, X3C, etc. What we're going to do here is we're going to label them a little more accurately so that we can see exactly what's happening. So our first one, X1A, is actually Cincinnati to New York. Our second is Cincinnati to Dallas. And our third, Cincinnati to Detroit. This is X1A, X1B, X1C. We can add that in too, just so we're clear. We'll continue that, so please bear with me for 1 second. And again, the last one. Oh, sorry, I made a mistake here. Okay. And the last one, we're moving from Pittsburgh we'll make this one a little bigger. Okay, what we've done is we've entered all of our information. The only reason I included the titles was because in real life, if you were presenting this to an important person, someone who was involved in this information, they don't want to see X1A. They want to see what those shipping routes actually are. So this is just a transformation of the variable name to make it a little easier to comprehend. Next, because we're trying to minimize our shipping costs, that's what we add now. $16, $18, $11, $14, $12, $13, $13, $15, and $17. That information was given to us, and that was given to us in the table from the example I covered in the first section. It's up to you, hopefully, to be aware of what was happening there. When we add our constraints in, the important thing is we name them appropriately. So this first one is TVs available Cincy. And that is X1, X2, X3 must be less than or equal to 300. What? Oh, no. So what we've done here is we've shown that TVs shipped from Cincinnati to New York, Cincinnati to Dallas, and Cincinnati to Detroit must equal less than 300. If it's more than 300, those TVs don't exist. This is not a viable answer. Next one, TVs available, Atlanta. 1, 1, 1 must be less than or equal to, 200. And that was given to us in the question. Finally, TVs available, Pittsburgh, must be less than or equal to 200. And we can see here, that means Pittsburgh to New York, Pittsburgh to Dallas, and Pittsburgh to Detroit must be less than or equal to 200. You cannot ship more to New York, more to Dallas, or more to Detroit than the maximum 200 that exists in the warehouse. So our fourth constraint was TVs demanded. So TVs demand New York. And so here we have 1A, 2A, 3A must be equal to 150. What we've said here is that TVs from Cincinnati, TVs from Atlanta, and TVs from Pittsburgh, all to New York, must only equal 150. Anything else is unacceptable. We repeat again, TVs demand Dallas. And here we have Cincinnati to Dallas, Atlanta to Dallas, and Pittsburgh to Dallas must equal 250. Finally, TVs demand in Detroit, so Cincinnati to Detroit, Atlanta to Detroit, and Pittsburgh to Detroit. If we name our columns like this, it's much easier to see what's happening. The total from Cincinnati to Detroit plus Atlanta to Detroit plus Pittsburgh to Detroit can only equal 200. That's all that they are asking for. Anything less, anything more is unacceptable. So what we've done is we've taken the graphs given to us in the problem and we've converted them to mathematical equations while reading the problem, and then entered those equivalent equations into QM. Now, all we do, once this has been done, all the hard work is over. The computer we will allow to solve this for us. We hit solve, and let's see what happens. What we see is our optional choices are to ship 200 from Cincinnati to Detroit, 200 from Atlanta to Dallas, 150 from Pittsburgh to New York, and 50 from Pittsburgh to Dallas. Let's see if that adds up. So in this situation, how many are being shipped? And in this situation, that would cost us a total of $7,300. Any deviation from this, any other shipping choices, will either break one of the first three or one of the second three constraints, or cost more money. This is given those three warehouse situations and given the amount demanded at each of the 3 locations, this is the minimum amount of money, given these shipping prices, that we can possibly spend to satisfy all 3 locations. All right, hopefully everybody's clear. I'm not going to give any homework today because on Thursday, I'll review this question one more time, but I'll review it in Excel because we're starting to move into a place where Excel might be easier than QM. So hopefully until now you've understood what we've done, and then as we move into the future, hopefully it becomes more clear when we get more complicated. Thank you everyone for listening. As always, if you have any questions at all, please do not hesitate to contact me about these problems. Thank you again. Hopefully we're very clear. I'll see all of you next week. Enjoy your weekend.